is we write cos t equal to 1 minus tan square t by 2 divided by 1 plus tan square t by 2, and then if we substitute tan of t equal to u, then we can easily solve to get tan inverse t by 2 equal to x plus c. Again, t is equal to x plus y. So the final solution of this differential equation is tan inverse of x plus y divided by 2 equal to x plus c. Thus we have seen that through a slight modification, through the substitution, that is x plus y equal to t, we have reduced this differential equation to a form that can be easily solved through the method separable variable, and thus we get this final answer. The next type of method is for homogeneous differential equations of the first order. So any equation of the form dy by dx equal to f1 of x comma y divided by f2 of x comma y, where f1 and f2 are the homogeneous functions. Now what is a homogeneous function? Homogeneous function is a function such that the addition of the exponents of x and y is constant throughout. So differential equations of the form of homogeneous functions of first order can be solved by using this method. Now we write dy by dx as equal to f of x by y by dividing both the functions by x to the power of n. So if this equation is of the degree n, then what we do is we divide the numerator and denominator by x to the power of n, and thus we express dy by dx as a function of x by y. In the next step, what we do is we substitute y by x equal to t, and so this is the way we solve such kind of homogeneous differential equations of the first order. So let's try to see an example. Solve the differential equation dy by dx equal to x square plus y square divided by 2x square. So dy by dx is equal to x square plus y square divided by 2x square. Now we see that the numerator and the denominator both are some functions and which are homogeneous in nature. This is because the exponent of x is 2, the exponent of y is 2, and the exponent of denominator is also 2. So this is a homogeneous equation. Now what we do is we write y equal to t times x. So dy by dx would be equal to t plus x times dt by dx. So dy by dx is equal to t plus x times dt by dx. We substitute this value over here to get t plus x times dt by dx equal to 1 plus t square by 2. This is because we substitute y equal to t times x. X and x gets cancelled from the numerator and denominator, and what we get is 1 plus t square by 2. So taking t to this side, we get 2 times x into dt by dx equal to 1 plus t square minus 2t. We bring this term to this side and we bring x and dx to this side of the equation to get 2 times dt by 1 plus t square minus 2t equal to dx by x. Now this could be written as t minus 1 whole square, and so when we integrate both sides we get minus 2 by 1 minus t equal to ln x plus c, because the integration of 1 by x is ln x. Again we write the value of t as y by x, so minus 2 by 1 minus y by x is equal to ln x plus c, or 2x equal to x minus y into ln x plus c. Thus the solution of dy by dx equal to x square plus y square divided by 2x square is 2x equal to x minus y into ln x plus c. The next method is equations reducible to homogeneous equations. Now we won't be getting equations that are directly homogeneous, but we reduce those equations to a form that could be easily solved, and that form is the homogeneous equations. So the differential equation of the form dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2. So if we have a differential equation of this form, then we use this method to solve it. Now your condition is if a1 by a2 is not equal to b1 by b2. So the ratio of coefficients of x is not equal to the ratio of coefficients of y. In the next step, what we do is we write x equal to capital X plus h and y equal to capital Y plus k. Now what are h and k? H and k are nothing but the points of intersection of these two lines. This is an equation of line and this is also an equation of line. So h and k are such that a1h plus b1k plus c1 equal to 0 and a2h plus b2k plus c2 equal to 0. So what we do is we solve these two equations to get the values of h and k, and hence we substitute here. Therefore dy by dx would be equal to d of capital Y by d of capital X. Therefore the equation becomes dy by dx equal to a1 into capital X plus b1 into capital Y divided by a2 into capital X plus b2 into capital Y, and thus becomes a homogeneous equation. Once again, For equation of the form dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2 can be reduced to a homogeneous equation, the condition here is a1 by a2 should not be equal to b1 by b2. So what we do is we solve these two equations and find the points of intersection. Let us say they are h and k. We put small x equal to capital X plus h and small y equal to capital Y plus k. So dy by dx would be equal to d of capital Y by d of capital X, and hence the equation reduces to d of capital Y by d of capital X equal to a1 into capital X plus b1 times capital Y divided by a2 times capital X plus b2 times capital Y. Now this is a homogeneous form and which can be easily solved. Now if we say that a1 by a2 is equal to b1 by b2, in the previous case we considered a1 by a2 is not equal to b1 by b2. Now in this case let us say that they are equal, and let us say that they are equal to lambda. Then dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2 would be equal to lambda times a2x plus b2y plus c1 divided by a2x plus b2y plus c2. So what we do is we substitute a2x plus b2y equal to t. Now the equation reduces to a variable separable form. So let us start to see an example. Solve the differential equation dy by dx equal to 2x plus 9y minus 20 divided by 6x plus 2y minus 10. So the differential equation is 2x plus 9y minus 20 divided by 6x plus 2y minus 10. Now we here see that the differential equation is not of the homogeneous type, but it is of the form that can be easily converted to a homogeneous form. How? Let's start to solve this. The lines 2x plus 9y minus 20 equal to 0 and 6x plus 2y minus 10 equal to 0 meet at the point 1, 2. If we solve these two equations, we get the point of intersection as 1, 2. We therefore make the following substitution. Small x equal to capital X plus 1 and y equal to capital Y plus 2. So the equation transforms to d of capital Y by d of capital X equal to 2 times capital X plus 1 plus 9 times capital Y plus 2 minus 20 divided by 6 times capital X plus 1 plus 2 times capital Y plus 2 minus 10. So this would be equal to 2x plus 9y divided by 6x plus 2y. So dy by dx, that is d of capital Y by d of capital X, is equal to 2 times capital X plus 9 times capital Y divided by 6 times capital X plus 2 times capital Y. Now this is a homogeneous equation, and when you solve it you will get the solution as 2x minus y whole square equal to c times x plus 2y minus 5. Thus very easily we have solved this equation. Now the next important type of differential equation is the linear differential equations. Now these are very standard differential equations, and most of the times these differential equations are asked. So this is of the form dy by dx plus p times y equal to q. Here p is the function of x and q is also a function of x. So any differential equation of this form is called as the linear differential equation. So dy by dx plus p times y equal to q, where p and q are functions of x, is called as a linear differential equation. But now what's the procedure to solve such a differential equation? What we do is we multiply both sides by e to the power of integral of p times dx. Here p is the function of x and is the coefficient of y. So what we do is we multiply both sides by e to the power of integral of p times dx. So the equation becomes e to the power of integral of p times dx into dy by dx plus py equal to q times e to the power of integral of p dx. Now this could be further written as e to the power of integral of p dx into dy by dx plus y times d by dx of e to the power of integral of p dx. Now this is because d by dx of e to the power of integral of p dx is equal to p times e to the power of integral of p dx. So this further reduces to d by dx of y into e to the power of integral of p dx. So this entire term becomes d by dx of y into e to the power of integral p dx. Now this is equal to q times e to the power of integral p dx. Now integrating both sides we get y into e to the power of integral of p dx equal to, let us say that the integral of this is some function of x, say r. So is equal to r of x plus c. C is constant of integration. So R of x is nothing but integral of q into e to the power of integral p dx, or r dash x equal to q into e to the power of integral p dx. Now what is this e to the power of integral p dx? This is called as the integrating factor. Your p is the coefficient of y, that is, it is a function of x but is a coefficient of y. So e to the power of integral p dx is known as the integrating factor, and hence the complete solution of the differential equation is y into the integral factor is equal to the integral of q into the integral factor. Thus we can say that the complete solution is y into integrating factor equal to the integral of q into integrating factor. So we have seen how to solve a linear differential equation, but it is incomplete until we solve an example. So solve the differential equation dy by dx plus cot x into y equal to cos x. So we clearly see that this is a linear differential equation. This is of the form of dy by dx plus p times y equal to q, where p and q are functions of x. So dy by dx plus cot of x into y equal to cos x. Now we see that p is equal to cot x, q is equal to cos x. So the integrating factor is e to the power of integral p dx. So this would be equal to e to the power of integral of cot x. Now integral of cot x is nothing but ln sin x. So this would be equal to e to the power of ln sin x. And so e to the power of ln sin x is nothing but equal to sin x. And thus integrating factor is equal to sin x. Also q into e to the power of integral p dx would be equal to q is cos x and integrating factor is sin x. So this would be equal to cos x into sin x. Therefore integral of q into e to the power of integral p dx would be equal to integral of cos x into sin x dx. Now to solve cos x into sin x dx, what we do is we make a substitution that sin x equal to t. So cos x dx would be equal to dt, and hence this would become integral t dt, the integral of which is 1 by 2 into t square. We write t equal to sin x here to get this as equal to 1 by 2 into sin square x. Thus the solution is y into sin x equal to 1 by 2 into sin square x plus c, or we can write y equal to 1 by 2 into sin x plus c times cosec x. Thus this is the solution of the differential equation dy by dx plus cot x into y equal to cos x. So what we have done here is we have multiplied it with the integrating factor. The integrating factor becomes sin x, and through that we have solved this differential equation. The next form is equations reducible to linear differential equations. Just now we have seen how to solve linear differential equations. Now there might be situations where a linear differential equation is not directly given to us, but actually is in a different format. So we try to convert or reduce such type of formats to linear differential equations. So the first is, if the equation is of the form r of y into dy by dx plus p of x into s of y equal to q of x. Now we see that this part is a function of y, this is a function of x, this is a function of y, this is a function of x again. If we have this equation in such a way that ds by dy is equal to r, here s is a function of y. So if we differentiate s with respect to y, we get the function r, which is the coefficient of dy by dx. Then what we do here is we put s of y equal to t. Therefore dt by dx would be equal to ds by dx, or we can write it as ds by dy into dy by dx. Now ds by dy is nothing but equal to r, so dt by dx would be equal to r times dy by dx. Thus we can write r times dy by dx as equal to dt by dx. Thus the equation reduces to dt by dx plus p of x into t